Okay, so we're continuing our discussion about linear algebra, and we're finishing it off now with some reminders about eigenvectors and eigenvalues. And so let's start things off here with a definition. If a times v is equal to lambda times v, where v is not equal to 0, then lambda is an eigenvalue of a, and v, you can think of v as kind of a corresponding eigenvector. Now it's important that v is not the 0 vector, right? And also, let's see if we can ask one question. Can A be a non-square matrix? No, because the output of the matrix, or your input and your output, have the same dimension, right? So in this case, A is n by n. And we're also going to see that sometimes A doesn't have an eigenvector and eigenvalue. Let's see. I'm going to write that. Okay. I guess maybe I'm jumping the gun on that. We can take a look to see what happens later. All right. So we're trying to solve this equation for v and lambda. So that's where we start. A times v equals lambda times v. Go ahead and bring the lambda over. And so this means that we're solving for the homogeneous part of the solution, right? So then we can factor this out. Right, and so just to double check, right, that ends up being the same as that. And so now we have this equation here. When does this have a solution? Well, if the columns of a minus lambda I are independent, right, then the only solution is v equals 0. And so we don't want that. We want non-zero solutions. So to have v not equal to 0, we must have the determinant of a minus lambda I must be equal to 0, right? Because that means that a minus lambda I is not invertible, right? And so that's our key equation here. Because this turns out to be a polynomial of degree n in lambda. Right, and so we can solve the polynomial of degree n for the n solutions, and then hopefully we can continue from there. Okay. By the way, does anybody happen to remember the name for that equation? Did you say characteristic equation? All right. So once you've found your polynomial of degree n, you set it equal to 0, of course, and solve. And for each lambda, you have to go back to the original set of equations and solve a minus lambda I times v equals 0. Okay, now I should say when we're doing this by hand, we're just going to be doing 2 by 2 matrices, because otherwise it gets to be a real kind of a pain. Later on we'll be using some software to do this. We'll be taking a look at Octave Online, and I'll give you more information about that later. We can also use Python or R, whatever your favorite piece of software is. I'm using Octave Online because it's a copy of MATLAB, which is really popular with engineers. And so if you're going to be going into any kind of engineering program, it's nice to know a little bit of MATLAB code. And so we'll talk about getting into the octave language in just a bit. Today we're just doing a little review here. So let's suppose that A is equal to 3 minus 1, 4 minus 2. Okay, then we take A minus lambda I. If it's been a while since you've done these, I'll go ahead and do it out here. But what you end up doing is just taking it from your diagonal elements here, subtracting lambda. Okay, and so then the determinant of A minus lambda I is going to be 3 minus lambda times minus 2 minus lambda minus 4. And let's see, can we simplify that a little bit? Minus 2 lambda, oops. Okay, so we just expanded that out and solved. And so hopefully this factors. It shouldn't be too bad, and in this case it does. I believe lambda equals 2, and lambda equals minus 1. Alright, so now for each of these we have to solve the system of equations. So for lambda equals 2, for example, we'll take a look at our 3 minus 2 v1 minus v2 equals 0, and then we have 4 v1 minus, maybe I'll say plus 2 minus, or plus, my notation is going to get messy here. I'll just go ahead and put the minus 2 in there. v2 equals 0. Good. Oops, that's 2 there, right? And so simplifying that, you see that we get v1 minus v2 equals 0, or 4v1 minus 4v2 equals 0. And so you see that these are the same line. Should they be? Yes, they should. And so really you only need to use one equation to solve that. And so what set of v1 and v2 satisfies this system? Well, you could say v1 is equal to v2, right? And then v2 is our free variable, v2 equals v2. So the vector is 1, 1, or any multiple of 1, 1 would solve this system. Good. And so that gives us the eigenvector for lambda equals 2. Okay, so similarly we can do the eigenvalue for lambda equals minus 1. So that'd be 3 plus 1 times v1 minus v2 equals 0. Now, as a shortcut, I'm not going to compute the second equation because I don't need to. Now, I could, if I had time, compute the second equation just to make sure that these are constant multiples of each other. But in this case, it's not necessary if I'm fairly confident in my answer. Hey, I'm confident in my answer. Good. And so now, as a shortcut for v, right, since we're in R2, you could just reverse your numbers here. And so if you have like a 1 and a 4 for your v, right, you can see that that's going to solve that equation. Good. You know, in general, you would have to go through and actually write down the full solution to this system of equations. But since we're only in R2, you're only going to get one vector, so it's not a big deal. Good. We have our eigenvectors and our eigenvalues. You might try one with R3. We're not going to get too far into that. I should say, when do we run into trouble? Well, one case where we run into trouble is where we have multiplicity. So what I mean by that is, consider the matrix A, which is 1, 0, 0, 1, versus the matrix A, which would be 1, 2, 0, 1. Okay, in both cases, lambda equals 1 and 1. So this says that the algebraic multiplicity equals 2. So algebraic multiplicity equals 2. But now if we go through and solve for a minus lambda I equals 0, in this case we just have 0v1 plus 0v2 equals 0, and 0v1 plus 0v2 equals 0. And so this is true no matter what v1 and v2 you choose. And so you could just choose the standard basis vectors for all of R2. And so in this case we only had one. You can think of this as a double eigenvalue, and we also got a double eigenvector, or two eigenvectors that are linearly independent. So this is the geometric multiplicity, geomultiplicity equals 2, but that's not always going to be the case if you have algebraic multiplicity greater than 1. So in this case we have 0, 2, let me rewrite that. 0v1 plus 2v2 equals 0, and then 0v1 plus 0v2 equals 0. Right, the second one's not going to mean anything. You only have one eigenvector now, 1, 0. And so the geomultiplicity equals 1, and this is where the problem comes in. When the geometric multiplicity, I guess I should be pointing at this one. Let me get this one out. When the geometric multiplicity is not equal to the algebraic multiplicity, not equal, then we're going to run into trouble with our solutions to a system of differential equations, but we'll deal with that later. Okay, for right now we're just doing a little bit of review of the linear algebra, and so in the next video, or in the next, let's see, I guess that's Friday, we're finally going to get into some modeling. Yay! See you then.